All right, thank you. Yes, today I'm going to be talking about some exchange correlation functionals. And in general, what we would like to calculate is the true many-body energy. And what we do here, for example, is the Hartree approach. And it has a number of problems. And what we do in DFT to kind of solve these problems is we introduce this kind of exchange correlation energy where we just more or less define it as all the errors that we make in these first three terms, we just subtract here so that in theory it is correct. The kind of trick is in how to do it and how to get the exact exchange correlation energy. And so, for example, when you do the Hartree approach, one obvious error you're doing in the Hartree energy is when you only have one particle, then this electron still interacts with itself, which physically makes no sense. And so this Hartree energy has what's called self-interaction. And so the first thing you want in the exchange correlation is a self-interaction correction. And then the exchange correlation energy usually is split into two parts. The exchange, which is just due to the Pauli principle, and the correlation is all other things where electrons interact, screening, self-interaction correction, whatever you can think of. And even though the magnitude of this term is comparatively fairly small, it's still quite important because this term causes the electrons to kind of be pushed out of the atoms and to participate in the bonds. And so if you don't have it, you can't accurately model bonds. So you will make large errors. And well, the easiest kind of approximation you can make is the kind of local density approximation, where you just say, if I have a given density at a certain point of space, I will map this density onto the homogeneous electron gas with the same density where I have the uniform density throughout the whole system. And then I will use the exchange correlation energy of the homogeneous electron gas at that point in space. And we can calculate this the exchange correlation energy of this uniform electron gas with a number of means. By now, most of them use some quantum Monte Carlo to interpolate it. And there's a number of approximations, but in the end, they're all the same. They all model the same number, the same function. And as you might imagine, this is the exact solution for the uniform electron gas. So when we use this approximation, we can. This is the correct ground state density. But here I calculated silicon, and as you can see, it's not uniform. I don't think that's the word to use. It's actually very well, almost chaotic. And the question is, does the LDA help us with this at all? And if you calculate, for example, the lattice parameter, it turns out, yes, here we have silicon, and it underestimates the lattice constant of silicon by about 0.5%, which is surprisingly good, actually. So overall, the LDA usually underestimates the lattice constant by about 3%, and it overbinds. So it has a bias towards smaller lattice constants. And considering the crude approximation we have made, we kind of have to ask ourselves, why does it work so well? And people have studied this a lot. And what you can do is you can rewrite the exchange correlation energy as kind of this Coulomb-style integral of the density and the exchange correlation hole density. And for this exchange correlation hole density, there are a number of constraints known. And the LDA fulfills some of these. So the exchange correlation hole has to be negative. And if you integrate over the exchange hole, it turns out that around one electron is missing. So if you integrate over the exchange hole, it turns out you have to be -1. And the correlation integrates to 0. And the reason the LDA fulfills these is that the LDA is based on a possible physical system. And this system fulfills the exact constraints for this exchange hole. And since the LDA is based on this system, it also it inherits this property. We can calculate more things with the LDA. So for example, we can also calculate band gaps. And here it's a different story. So we get somewhere an estimation from -20 to -100. So I think germanium is metallic where it shouldn't be. Or we have this one is a weird one. And in the end, you have an error of about 1 eV, which is, if you, for example, want to calculate solar cells, this is not good enough. So this is a huge error. And we have to ask ourselves, how can we improve upon this? And, well, one of the classics idea in physics is to just do some kind of Taylor expansion. So we can include the gradient of the density in addition to the density. And then we go from a local approach to kind of a semi-local approach, where we kind of get the surrounding area of our point in space by introducing the gradient. And I told you there's one LDA with a few parameterizations. This is not the case for GGAs. So GGAs are not uniquely defined. There's a large number of GGAs. And because there's such a large number of GGAs, it's not strictly ab initio. So you have to the parameter of the choice of the GGA. And in FLEUR, we have a number of GGAs. Actually, we have 5. So we have this Perdue-Wang 91, and we have a number of PBEs, where the PBEs, they're just slight revisions. So I think there's one parameter slightly different in between these and this, then is the revision of this one. And the people that developed this octopus code, they have published a library, the libxc, and they have 125 GGAs. And for example, they have PBE Sol, which is also quite interesting. And we recently implemented an interface to this libxc, and so now FLEUR also has 125 GGAs. And if you want to use the libxc, the first thing you have to do is you have to recompile FLEUR, and you have to give it this -libxc true flag, and then our configure script will download libxc and compile it. So it's fairly straightforward. And the second thing is you have to replace the usual exchange functional tag with some tag that is somewhat longer. So the name is then libxc, where you have to make sure to spell it with a capital A and a capital XC. And you have to add this kind of subtag where these names are just the names that the libxc uses. So you can check it on their website if their website works again. And well, how do these GGAs perform? So we went through all the effort of including gradient. Does it help us? Well, if you look, for example, at the PBE actually overcorrects the lattice constant. So now the PBE has a bias towards too large lattice constants. But it actually improves, still the mean improves by a factor of 2 roughly. And in the libxc we also have the PBE Sol, which is basically the PBE. But when they designed the PBE, they designed it with molecules and atoms in mind. And when they redid it for the PBE Sol, they used some constraints are based on crystals rather than molecules. And the PBE Sol actually reduces this kind of bias the PBE still has. And it's a slight improvement over the PBE. So if you really want to calculate crystals, this is an easy win without any additional effort. And for the band gap, the PBE doesn't actually improve on the LDA. So it's still more or less 1 eV off. It's a slight improvement, but it doesn't help us. But if you check in the libxc, there's also this EV93. And so then you combine the EV93 for the exchange. And for the correlation, you use this Perdue-Wang 91. And this was designed with band gaps in mind. So I wouldn't necessarily trust it for any other properties. But they designed it so that it improves the estimation of the band gaps. And it does. So it is, the band gaps are better. So for example, germanium now is actually a semiconductor rather than a metal. But it's still not great. So if you really want to design solar cells, half an eV is still a lot. So GGAs are not capable to give us accurate band gap predictions. And there are other problems. So for example, here I calculated graphite. And graphite consists of these kind of graphene layers that are weakly van der Waals bonded. And so what I did here, I kind of varied this C parameter to see kind of the distance in between these graphene layers. And it turns out that PBE overestimates it by about 30%. And once again, you can have a look in the libxc and you find some functional. And I think this B97D is supposed to improve these van der Waals forces. And it does. So it underestimates it by about 10%, which is better than 30%, but it's still not great if you compare it, for example, with the performance of an LDA for a normal metal or something. And so if you want to do van der Waals calculations, you have to go to these proper van der Waals functionals that are not semi-local as the GGAs. So these usually consist of a GGA exchange, some LDA correlation, and then you have an additional term, this non-local correlation, where here you have just this local term that only depends on R. But this non-local term basically combines the density of R and R prime through this van der Waals kernel. And to capture the dispersion in a meaningful way, you have to have this non-local term. FLEUR has this feature, but it's currently not properly documented. So if you're interested in using it, feel free to contact us. So, so far I've told you about two kinds of functionals. I've shown you the LDA, and if we include the gradient, we get the GGAs. And in order to further improve it, there's a number of methods, and Perdue kind of arranged them in this ladder to DFT heaven. And the next step would be to include the kinetic energy density, where you use these, where you have some orbital dependence. And then you go to non-local functionals. So here they start to depend on R prime. And beyond this, I think Christoph is going to introduce you to this. But this is slightly misleading when you consider computational effort. The first three are in FLEUR more or less indistinguishable because they're semi-local and the potential part takes maybe 5%, if at all, of the total time. And so you won't really notice which one you use by the computational time. But if you go to hybrid, if you go to the non-locals, there's a big step, and this is a significant additional computational effort. So I've shown you the GGAs, and well, we have to consider how to improve upon this. So how can we go beyond GGAs? And when they designed the PBE, the reason the PBE is so successful is I showed you that the LDA fulfills by design a number of constraints for this exchange correlation energy. And when they designed the PBE, they used this additional freedom they got by introducing the gradient. They used this to fulfill more of these constraints. And for the meta GGAs, they introduced another variable, and they had more freedom. And there were two attempts to fulfill more constraints, but finally they were successful with this scan functional, which fulfills all known constraints. And it is a significant improvement over the PBE. So when the LDA is when the PBE is a factor of 2 better than the LDA, scan also roughly is a factor of 2 better than PBE, and it at almost the same cost. And we have scan in FLEUR, and it's implemented through this libxc interface. And yeah, if you're interested in using this, yeah, feel free to contact us. As nice as these meta GGAs seem, they do have a disadvantage. So if you want to calculate the exchange correlation potential, what you do is you just take the derivative of the energy with respect to the density. And if you go to the GGA, you have an additional term because it depends on the gradient. You also take the derivative with respect to the gradient. For the meta GGA, you also get one additional term, but this term isn't as trivial because the kinetic energy density actually depends on the orbitals rather than the density. And so it's not straightforward to apply this. So there are some methods such as the OEP But what we did in FLEUR actually, when we calculate with scan, we calculate the exchange correlation energy in a scan, and we just calculate the potential in PBE. And this is quite common. A number of codes do this, and it is still very successful. So this table I showed you here, I think it's the Wien2K code, and they also do it without OEP, and they still get this improvement. And but there's another class of meta-GGAs where they just circumvent this whole problem I explained to you here. They actually, rather than giving you the energy, the exchange correlation energy, and the derivatives with respect to its ingredients, they just give you the exchange correlation potential directly. And even though this is, theoretically not necessarily the cleanest way to do it, they use this to optimize the functional for specific properties. So, for example, here Tran Blaha designed a functional that is very accurate for bandgap predictions. And if you, for example, compare the LDA and the Tran Blaha and the HSE, you can see that that the Tran Blaha is significantly better than the LDA, and it almost performs as good as the HSE. And but you have to consider that it's still a meta-GGA, and that HSE is a hybrid functional, so it has a significantly more computational cost. So these are the meta-GGAs, and I'm sure you're all itching to see what's next. So the next step would be to go to hybrid functionals, and the motivation for this is I think Mariana introduced on the first day this Hartree approach, where you express the wave function kind of as a product of these orbitals. And the obvious problem with this is that if you have fermions, they are subject to this Pauli exclusion principle, and the Hartree approach does not fulfill this. So people then went to the Hartree-Fock approach, where rather than just expressing it as a product function, they express it as a Slater determinant, and then more or less by design you have exact exchange. But this is a 6-dimensional integral, so these calculating this Hartree-Fock exact exchange is computationally quite heavy. And but the Hartree-Fock isn't perfect, so it has a number of problems. And one of them is that in the end you express the wave function as the linear combination of the products of these orbitals. And in the end this means that the density of two particles is just the product of the densities of the two particles individually, which means they're not correlated. So the densities are uncorrelated, but we have this nice exact exchange. And on the other side we have these Cohen-Charm equations, where we have a good correlation but no exact exchange. And I think you can all see where this is going. We just combine them. So there are two kind of approaches to combine them. There's this one parameter approach where you mix exact exchange with some Cohen-Charm exchange, and then you take the Cohen-Charm correlation. But particularly in quantum chemistry, there's this 3-parameter approach is quite popular, where they mix some LDA, some GGA, and some exact exchange. And well, we have to spend more computation time on this. Does it help us? Well, if you look at this, for example, you can see that the lattice constant for the PBE0 or the HSE is much better than the PBE. So it does help us. But more interestingly than the lattice constants are these is the band gap, because here we actually see is for the first time we see some accurate predictions of a band gap. So here we have a mean error of about a quarter of an EV, or 0.16 EV, which is much better than what we saw with the PBEs, which were around 1 EV. And both of these are implemented. And again, if you want to use them, feel free to ask us. And with this, I would like to conclude my talk. I've shown you a confusing amount of functionals. Some properties we can describe well in local, in semi-local or local functionals. Some properties we can't. And if you want to describe these properties, you have to use some more expensive methods, such as hybrid. And with all this in mind, It's always important not just to get the right results or the results that you hope to get. You want to get the right result for the right reasons. And if you are wondering why I haven't talked about the last step or the next step in Jacob's ladder, this is because I think the next talk is going to touch on this. Thank you very much.